Hello, hello. Time to start. So, welcome to the Friday colloquium. Our speaker today is Shira Zerbib. She got her PhD in Technion in Israel, and now she is a postdoc at the University of Michigan, and she will be speaking about colorful coverings of polytopes.
Thank you very much. And thank you very much for inviting me to speak here today. It's a pleasure. My first time to Iowa, and so far it seems great, and the hospitality is perfect, so thanks a lot.
Could you
And
speak louder, please?
yes, I'll try. And indeed, I'm going to talk about colorful coverings of polytopes, and this is a joint work with Florian Frick. So let me start with presenting three seemingly unrelated problems. So the first one is going to be the following. So let us first recall a lemma that is pretty much famous, at least for people that work in combinatorics and topology, and this is Sperner's lemma from 1929. So we start with the k-dimensional simplex. So for example, here we have a two-dimensional simplex, delta 2, and it has vertices 1, 2 to k plus 1, or 2, 3 in this case. And we're given any kind of triangulation, T, of this simplex. So we are adding some vertices somewhere, and we are taking any triangulation that we want of this simplex. And now we have also a labeling function of the vertices of the triangulation. What does that mean? To every vertex in this triangulation, so these are the vertices of the triangulation, we give some number between 1 to k plus 1, or to 3 in that case. And the way we give number, we cannot just assign numbers as we wish. We have some nice labeling property. And the property is that vertex 1 must be labeled with number 1. Vertex 2 must be labeled with number 2. The face 1, 2, so this edge, must be labeled with either 1 or 2. So you can say something like that. The face 2, 3 must be labeled with either 2 or 3, whatever we want. And here again, we can label with either 1 or 3. And inside, we can label as we wish. Say, I don't know. Then Sperner's lemma promises us that however we do this, as long as we keep this nice labeling property, we can find a simplex in the triangulation that is labeled by all distinct colors or all distinct numbers. So let us see here, for example, we have this simplex and it is labeled by 1, 2, and 3. Okay, this is Sperner's lemma. A somewhat less known brother of this lemma is the KKM theorem. And this is from 1928. And this is due to Knaster, Kuratowski, and Mazurkiewicz. And here again, we have the simplex, the k-dimensional simplex. So for our purposes, it's going to be delta 2. And again, we have those vertices, 1, 2, k plus 1. And now instead of a labeling and a triangulation, which is something of discrete nature, we have something else which is of continuous nature. So we have closed sets indexed by the vertices of the simplex. So in this case, we have 3 closed sets. And these sets cover our simplex but not just any cover, but the cover must have some nice property to it. And what is this property? So again, vertex 1 must be in the set A1. I'm drawing it like that, but the set doesn't have to be nothing. It has to be closed, but it doesn't have to be convex or even connected or anything. But just for the sake of the example. So vertex 1 must be in A1. Vertex 2 must be in A2. And the face 1, 2 must be in the union of A1 and A2. So we have something like that. And similarly, vertex 3 must be in A3. The face 1, 3 must be in the union of A1 and A3. And the face 2, 3 must be in the union of A2 and A3. So we have something like that. If we want to write this condition mathematically, it's just writing that every face sigma is contained in the union of the AIs, where I is a vertex in sigma. Okay, this is just writing this condition. KKM tells us that once we have such a cover, such a KKM cover, then we must have that the intersection of all the sets AI is not empty. Okay, so for example, we have here this point in the intersection. Okay, so this was just a background. So here is our first question, question 1, or problem 1. Now suppose that we have 3 different KKM covers of delta K, or delta 2 in this case, or K plus 1 different or maybe the same, K plus 1 KKM covers of delta K. Can we find a colorful selection of one set in each cover such that the intersection is non-empty? So let us write that. Suppose that we have AI, BI, and CI, 3 KKM covers of delta 2. Can one find some permutation pi in the permutation group on 3 elements such that A indexed with pi 1 intersection with B indexed with pi 2 intersection with C indexed with pi 3 is non-empty. Okay? Yes?
Could you just clarify what the sigma condition is, sigma subset of the union?
Yeah, this is just saying that this nice covering condition that I explained here holds. So the face 1 must be in A1. The face 1, 2 must be in the union of A1 and A2, and so on. Okay? And this is a colorful version of KKM. So let us call this question colorful KKM. When we think about those A, B, and C as 3 different colors, okay? And we want to take one of each and find a non-empty intersection. Okay, this was problem number 1. Here is problem number 2. So suppose we have 3 finite set of points in R2 in the plane. And we have the property that, or let us start with the non-colorful version. So suppose we have just one colorful, just one finite set of points in the plane. And we have the property that the point 0 is in the convex hull of our set X. Okay, so we have our point 0 here, and we have some finite number of points that hold 0 in their convex half. Then the Caratheodory theorem I think it was back in 1914, asserts that one can find 3 points in X already holding 0 in their convex half. So for example here, you can find this one, and this one, and 0 is in the convex half of these 3 points. Or in general, if we have the set in RD, then we can find D plus 1 points already holding 0 in their convex half. Okay, so now here is question number 2. So suppose that we have now 3 or D plus 1 finite sets of points. So here we have X, Y, and Z. And we have that the property that 0 is in the convex half of all 3 of them. So it is in the convex half of X and in the convex half of Y and also in the convex half of Z. And now the question is, can one find X in X, Y in Y, and Z in Z such that 0 is in the convex half of these 3 points? So can we find a colorful selection of 1 point from each set when we think about these sets as colors, such that 0 is in their convex half? And let us call this colorful Caratheodory. The third problem that I want to present is the following, also from the area of discrete geometry. Yes, question?
I'm just moving.
So let us fix some 2 segments on the real line, say, I don't know, 0, 1, and say 2, 3. Okay, these are fixed in advance. And now we define a 2 interval. It is just a set that is a union of 2 intervals. One is taken here, and the other one is taken here. So one on the first segment, and the other one on the second segment. This is just the definition. It's a set that is a union of 2 intervals. Now, a theorem of Tardos and Kaiser, and this is around 95 to 97, tells us the following. So suppose that we have a family F, a finite family of such creatures, of 2 intervals. So F is a family of 2 intervals. Now suppose that F has some property regarding the number of points needed to pierce it. So what does that mean? Suppose that every time I choose a point X here on the first segment and a point Y here on the second segment, I can find in F some 2 interval that is not pierced by any of these 2 points, that does not contain any of these 2 points. Suppose that I have such a family that has such a property. So we say in this case, suppose F cannot be pierced by 2 points. Okay. Then the theorem of Tardos and Kaiser promises us that we must have that F contains two disjoint two intervals. In other words, the theorem says that if we have a family of 2 intervals and each two intervals in our family intersect, then we can find 2 points that pierce all the elements in our family. Okay, and if you think about it, it seems reasonable when you start to work with examples, but it is not trivial to prove. And indeed it was a long-standing conjecture until Tardos proved it in 95 using topological methods, using the Borsuk-Ulam theorem. Okay, so now, question number 3. Suppose now that we have 2 families of 2 intervals. So we have F1 and F2. We still fix these 2 segments, 0, 1, and 2, 3. So everything happens in this world. And we have 2 families of finitely many 2 intervals. And both families have the property that they are not pierced by 2 points. Okay? Both cannot be pierced by 2 points. The question is, can one find F1 in F1, some 2 interval in the first family, and another 2 interval in the second family, such that these are disjoint, such that F1 intersection with F2 is that. Okay, so we want now a colorful version of the 2 intervals or the D intervals theorem. So let us call this colorful D interval. The D just comes from, instead of fixing 2 segments, we fix D segments, and a D interval is just the union of D intervals, one on each one of these segments. Okay, so we have 3 problems. What might be the connection between them, except for the word colorful? So what I want to show you today, that the positive answer to all 3 questions follow from the same topological theorem about colorful coverings of polytope that I will hopefully explain. But before we do that, let us discuss a little bit the history of each one of these questions. So a colorful version of the KKM theorem was proved by Gale in 1982, but we can also think about it as a fair division problem. So imagine that we have a rectangular cake and 3 players, A, B, and C, 3 people attending a party, and we want to split the cake into 3 pieces and assign 1 piece to each player in such a way that every player is happy with the piece he got, meaning that he does not strictly prefer the piece he hasn't got over the piece he got. Okay. So the entry-free division theorem promises us that given some conditions, this is actually possible. So there exists some partition of the cake into 3 pieces such that each one gets a piece and is most happy with the piece he got. Now, how does this relate to our problem? We can think about every point in delta 2 as a partition of this rectangular cake. How do we do that? We consider the usual embedding of delta 2 in R3. So a point here is just x1, x2, x3, such that the xi are non-negative and the sum of them is 1. We think about this rectangular cake as the 0, 1 interval. And now the partition that we assign to this point is just the partition where this piece, the first piece, is of length x1, the second piece is of length x2, and the third piece is of length x3. So every point here corresponds to a partition. Now we can think about the sets AI as the set of partitions in which players A prefers piece I. And similarly, the sets BI are the set of partitions, namely the set of points in delta, in which player B prefers piece number I. And similarly for player C. Now, the fact that the entry-free division theorem exists, namely there is a partition that satisfies all the player, exactly means that there is a point, there is a partition in the intersection of where player A prefer piece number pi of 1 and player B prefers another piece, namely pi of 2, and player C prefers another piece with it, which is pi of 3. Okay, so this can be interpreted as the entry-free division theorem. Yes?
I'm slightly confused about it because at least the proof I'm seeing of the entry-free division of a cake involves you like chopping up, people repeatedly chopping and moving pieces. Is
Right.
there a version of the theorem that actually says you can do it with like just intervals on the cake like that without like
No,
exchanging
the
pieces?
chopping, what you mean by chopping is just using the Sperner's lemma and taking finer and finer subdivision of it, and then using the fact that the sets AI are closed to claim that in the limit they all prefer a different piece. I don't want to get into the proof of the third division theorem, although I'm going to talk about this tomorrow in my other talk, so maybe there. But what the third division theorem tells us, the conclusion, without going into the details of the proof, is that if the players are hungry, namely they always want a positive piece over an empty piece, and if their preference sets are closed, then you can find such a partition. Okay? Such that everyone gets an interval or sub-interval of the unit interval. Colorful Caratheodory is, of course, the celebrated theorem of Imre Barany from 1982. And the third one, the colorful, the intervals, which should have been here. Is or was an open question before our theorem. Okay, so now let us try to state our theorem, and in order to do that, we should start with some story that starts with the KKM theorem, as I explained in 1928, and this theorem is equivalent to the Sperner's lemma, 1989, and both theorems are equivalent to Brouwer fixed point theorem, and equivalent is meaning that all three of them are easily proved one from another. And there was the colorful KKM in 1982. By the way, the fact that the colorful version of a theorem implies easily the non-colorful version of it is just taking all the different colors to be the same element, and then you get the non-colorful version. Okay, so in 1973, Shapley proved a powerful generalization of the KKM theorem. So this is Shapley in 1973, and this version is called the KKMS Theorem. So KKM and S stands for Shapley. So let us discuss the KKMS theorem.
It's under.
Thank you. So again, we have delta K or delta 2. And remember before we had the closed sets A1 to A3 that were indexed by the vertices. Now for each face of delta 2, for each sigma face of delta 2, we have a closed set A sigma. Okay, so we have closed sets indexed by the faces of delta 2. And these closed sets again cover delta K, again with a nice covering property. So what is this nice covering property now? It's going to be that vertex 1 must again be in A1, vertex 2 must again be in A2, but now face 1, 2 can be in the union of A1, A2, and A1, 2, because we have a set for the face 1, 2, the edge 1, 2. So we have something like that. Again, face 1, 3 must be in the, vertex 3 must be in A3, face 1, 3 must be in the union of A1, A3, and A1, 3. So we have something like that. And 2, 3 must be in a union of A2, A3, and A2, 3. And we might have also some A1, 2, 3 somewhere. To write this condition mathematically is just saying that every face sigma is contained in the union of a tau, or tau is a subface of sigma. So this is the same condition as here, But here we had non-empty sets only for the singletons. Okay, and here we consider any face here. So now it is no longer true that the intersection of all the sets is non-empty, as we can see even in this small example. But the theorem promises us that there exists sigma 1, sigma m that are balanced, faces that are balanced, and the intersection of the corresponding sets is not empty. So what does it mean to be balanced? It is something very intuitive. It just means that we can find weights alpha 1 to alpha m, non-negative weights, such that if we multiply these weights by the characteristic vector of these spaces, alpha m, then we get the characteristic vector of the entire simplex, which is just 1, 1, 1, k plus 1 times. Okay, so let us look at an example. For example, the faces 1, 2, 2, 3, and 1, 3 are balanced because we can give weights half to each vector, and this is just half times 1, 1, 0 plus half 0, 1, 1 plus half 1, 0, 1. And this sums up to 1, 1, 1, the characteristic vector of delta 2. And indeed, we see in this example that the intersection of A12, A13, and A23 is not empty. So the theorem promises us that we can always find such a set of faces, sigma 1 to sigma m, such that those faces are balanced, and simultaneously the corresponding sets intersect. Okay. Now an easy observation is that that sigma 1 to sigma m are balanced if and only if the barycenter of the simplex, the center of gravity of the simplex, is in the convex hull of the barycenters of these spaces. So let us look at an example. So we saw that 1, 2, 3, and 1, 3 are balanced. And indeed, we have that the center of gravity of the simplex is in the convex hull of the center of gravity of the three faces. And similarly, I claim that the face 3 and the face 1, 2 are balanced. Why is that? We can just give weight 1 to each and get the entire one vector. And indeed, if we take the barycenter of these two faces, it contains in its convex hull the center of gravity of the simplex. Okay? So these are just examples. So a restatement of the KKMS theorem is just that if A sigma is a KKMS cover, of delta K, then there exists sigma 1 to sigma m such that the barycenter of delta is in the convex hull of the barycenters of sigma 1 to sigma m, and simultaneously the corresponding sets intersect. And there is a colorful version of the KKMS theorem due to Shi and Li, and this is in 1994. Now in 1994 also, Kamiyama made far-reaching extension of this theorem, and he observed that we can actually replace delta K by any k-dimensional polytope P, and we can replace the barycenters by any points y sigma in sigma, and still the conclusion of the theorem would be true. So what Kamiyama tells us that if P is any k-dimensional polytope, and for each phase sigma of P, we are given a closed set A sigma and any point y sigma in sigma, then, and we have that this is a Kamiyama cover, and what is to be a Kamiyama cover? It is always the same thing. So a Kamiyama cover is just that a phase sigma is always contained in the union of A tau, tau a subphase of sigma. Then there exist phases sigma 1 to sigma m such that the point that we chose for the entire polytope is in the convex hull of the points that we chosen for these phases. And simultaneously, the intersection of the corresponding sets, the A sigma I, is non-M. Let us see an example of how to apply this theorem. So let us take the unit square. Let us take the unit square with vertices 1, 1, 1, 2, 2, 1, and 2, 2, just names, okay? And suppose that we have a Kamiyama cover of this square with 4 sets, A11, A12, A21, and A22. And the fact that it is a Kamiyama cover implies that this cover must look like that. So this would be A21, and this is A11, and we have also A12, and it is a cover. We have A22. So I claim that Kamiyama theorem asserts that either A21 intersection with A12 is non-empty, either these two sets intersect, or A11 intersection with A22 is non-empty, or these two sets intersect. So you cannot cover a unit square in such a way without having that one of the diagonal sets intersect. Okay? Why is that? Why does it follow from Kamiyama? Just take the barycenters again as your Y sigmas. Okay? So the only non-empty sets here are those. So in order to have the barycenter of P in the convex hull of the barycenters of the vertices, we must have that either those are the points that give that, and then their intersection is not empty by the theorem, or these are the points that give that, and their intersection is not empty by the theorem. Okay? Good. So now we are ready to say what we proved. So we proved a colorful generalized Kamiyama. This is Florian and myself in, I guess, 18. And so let me state the theorem and explain this generalized thing. So now we start with, again, P is a k-dimensional polytope. And we choose some yp, again, in P. Okay. So now, for every face, for every proper face sigma of P, we choose k plus 1 points y sigma I. Okay, so the I is indexed by 1 to k plus 1. So we have for every face a choice of the points y sigma I, where these points are not necessarily even in sigma, but if we have our polytope, and this is yp, and this is sigma, then we just demand that the points that are chosen for the face sigma is somewhere in the cone of sigma. So it doesn't have even to be inside this polytope. It has to be somewhere in this cone. So let us call this cone sigma. And for every face, we have also a closed set, a sigma I. So we have, again, k plus 1 Kamiyama covers of these polytopes. Then we can find faces sigma 1 to sigma k plus 1 now, such that the point that we've chosen for the entire polytope is in the convex hull of a colorful selection of points, a sigma 1, 1, y sigma m, sigma k plus 1, k plus 1, and simultaneously the intersection of the colorful selection of corresponding sets is non-empty. And the intersection of the ai sigma I goes from 1 to k plus 1 is known. Now this theorem is finally general enough to imply, of course, all these former results, but also the three applications that I showed in the beginning, and in particular the colorful T intervals, and also the colorful Caratheodory, and this gives a completely different proof to the colorful Caratheodory theorem than the one given by Imam Barany. And since in most of these applications the polytope that we use is not the simplex, and in at least some of these applications the the points y sigma that we use is not even inside the polytope, but somewhere here in the cone, then none of these applications are implied by any of those former KKM type theorems. Okay, so I don't have much time left, so I cannot show you how to derive all those applications, and also I cannot tell you much about the proof, but I do want to use some 2 minutes. Do I have 2 minutes left? To show you how to derive the colorful two-interval application from this theorem. So, colorful two intervals. So I remind you that we have two families of two intervals, F1 and F2, and both are not pierced by 2 points. So we want, and what we want to find is a choice of two interval here and a two interval here such that they are disjoint. Okay? So they are not pierced by 2 points. So every time I choose x here and y here, I find some F1 in F1 that is not pierced by any of these 2 points. So it is somewhere here. It does not contain x and y. And similarly, I find some F2 in F2 that again is not pierced by any of these points. So it is somewhere here, and it does not contain x and y. Now we can look at the unit square as the set of all points x, y that we can assign here, right? For every point in the unit square, x, y, we assign x here and y here. So this will be our polytope, the unit square. And I want now to use this property to build two Kamiyama covers of the unit square. How do I do this? So let us first build the first Kamiyama cover. So let us call this 1, 1, 1, 2, 2, 1, 2, 2. Okay, and now I want to tell you where to put the point x, y. Okay? So so remember I'm building Kamiyama covers A1, and here will be either 1, 1 or 1, 2 or 2, 1 or 2, 2. There are 4 sets. Okay? where do I put x, y? I take this x, y, I distribute the x and y according to their coordinates. I know that this does not pierce f1. The one here corresponds to the one here. Okay? I know that this does not pierce f1. So there is a red two interval that is not pierced. It is located somewhere. The first component of it either is located in the first subinterval or in the second. And also, the second is located either in the first or in the second. So in this case, it is located in the first here and the second here. So I put it in A1. 1 is for red. And 1, 2 for the positions of the two intervals that is missed. Similarly, and again, if there is another red two interval that is missed and is located in the second and second, then I put x, y also in A1, 2, 2 in this case. So this gives me a Kamiyama cover. It is very easy to see that it is Kamiyama cover. I want to explain why. This gives me a Kamiyama cover of this polytope, similar to the one that we saw in the example before. And similarly, I do the same for the second, the blue family here. So I get a blue Kamiyama cover of the unit square. Now, our theorem implies that we have either I 1, 1 intersection with 3 minus I 2, 2 is non-empty, right? This is the colorful version of what we saw before. Or A1, 2, I intersection A2, 1, 3 minus I is non-empty. This is just what the theorem gives us. Okay, suppose this is the case, okay? So suppose that we have that A1, 2, 1 intersection with A2, 1, 2 is non-empty. Okay, this is one of the possible outcomes. Then, okay, let us take these two. Let us take, sorry, these two, so these were not good. Let us take our two fixed segments. And now we know that this is not empty. What does that mean? It means that there is some x, y inside here, right? So let us put this x where it belongs and y where it belongs. Now we know that xy is in A1, 2, 1, meaning that there is a red two interval in this position. What is the position? The position is 1, 2. Okay? Now we know that this xy is also in A2, 1, 2. So there is a blue two interval that is in position 2 and 1. And we got that the red and the blue two intervals are disjoint, which is what we wanted to prove. And this proof generalizes to all D and all number of piercing points. So it's not just for 2 and 2. Okay, so thank you.
In your diagram here, so you have that KKM is equivalent to the Brouwer fixed point on the way bottom.
Yes.
And that's a statement in terms of like the behavior of a continuous function. Do any of the stronger theorems, do they have any equivalences that are in terms of the behavior of a function, or is that not, or that sort of phrasing doesn't work for the stronger versions?
Yes, so even if you look at our proof of the Kamiyama theorem, it is basically a fixed point. So it follows from a fixed point argument. It follows from